Okay, so hello everybody, welcome to the Prague seminar on function spaces. It's my great pleasure to introduce the speaker of today, Sebastian Schwarzacher, who is now an associate professor in Sweden at the University of Uppsala. And at the same time, he is the head of a research group on fluid structure interactions at the Charles University in Prague. And today he will give a talk on Rogowski type operators on time-changing domains. So, Sebastian, please.
Thank you very much, Anthony, for this very nice introduction. And thank you, Lukas, for this invitation.
You know, it's different title from the book.
Really?
It's a Rogowski estimate.
Yeah, well, I will tell what is the connection between this and the Rogowski operator. Yeah, so thank you very much for the invitation and also for this ad hoc possibility to speak personally here. Yeah, so I think I should use this, right? No?
Does it work?
No?
No, it works. Try it now.
Yeah. Okay.
You have to click it on.
So, yeah, we start by explaining what this is and why we do this. Okay, so here is like my situation, my setup. So this omega t, this is my notation, is a time slice of a domain which is in R1 plus n. You can see this. Use a stick or something.
Sorry, really?
Use the hand, yeah.
Okay.
No, I'm so used to this point.
I should ask for a pointer somewhere. Your arms are long enough.
Huh? Yeah, maybe I can just use. Maybe I can just use my hands. Yeah. Okay. So I think.
Do you want this red pointer, or should I ask the guy to bring it?
I think we can maybe I can have. Yeah.
Okay.
Yeah. Let's try. So anyway, so here this is the BF is what I will consider. Okay, so we have a domain in space-time. This is how it's to be seen. So one time dimension and space dimensions. And then we have like the omega t is like this, then the levels with coefficients. And the important thing is that the Rogowski operator is a space operator. So it is an operator which is acting on the space divergence. So it's the inverse of the space divergence. Here's like the definition. So essentially, you take a function f here, yeah, and this is now in a time slice here of omega. And then you want to find a function such that the divergence, which is the space divergence, is this function. So this is a derivative, yeah, the trace of the whatever, yeah, of the. So it's the divergence in space direction. Yeah? So you take the derivatives just in the n components of space, and you don't take a time derivative here. So there is like a certain mismatch here that we have a space operator, but we want to look at domains which are in time space. Yeah? And important thing is that we want to take even rough domains. So let me maybe make a picture here. So this is the time, this is the space, and then essentially the domain can look really horrible. And on each of these omega t's, we want to look at an operator that is inverting the divergence. Yeah? So this was the title. It was on the left inverse of the divergence. So we want to find something which inverts the divergence. And what is happening?
I was wondering if they can see it. The blackboard.
Aha.
Do we know how to do it? Počkej, no to nevím, zkus to, no prozej to, tady to kamera, celý to počkej, ne, spíš tady.
Hi. Yeah, so you can see it, yeah? More or less.
Bylo to tam? Jo, to je dobrý.
Okay. And so observe that the function f here is a scalar because the divergence of a vector is a scalar, but the operator will produce a vector. Yeah? So we take a scalar, we produce a vector, and maybe you can see already that actually this B, this is not a uniquely defined operator. You have many possibilities, yeah, because you have a one-dimensional object and you create an n-dimensional object. So lots of flexibility here. What makes the Bogovsky operator a Bogovsky operator, at least for my definition, is that the Bogovsky operator inverts the divergence such that the boundary value is 0. So we actually solve a boundary value problem, but a very ill-posed boundary value problem, if you wish. And by this boundary value, so you have this compatibility condition here in weak form. So this essentially means that the integral over f for every time instance has to be 0. And this follows by the fact that if you take like the divergence of the Bogovsky of f, which is equal to the integral of the f, of course, because the Bogovsky is the right inverse of the divergence. And if I'm now using Gauss theorem here, I get the boundary value of the Bogovsky in normal direction. And this is 0 because we want to have a 0 trace. This is what makes the Bogovsky operator. So we need that the mean value is 0. And because this is a space argument, this actually has to work for each t. And this is this compatibility condition here. So this is something we have to require. It can be very annoying, but yeah. What is sort of an important first observation here is that every Bogovsky operator is a dual of minus the gradient. Yeah. So you can always, like when you have a Bogovsky operator, you can sort of have this chain of equalities, and you see that the B star is left inverse then of the gradient. Yes. So this is what one should always keep in mind. And now you see also the flexibility, while the gradient gives the full information of the function except for a constant. Yeah. So if we fix this constant here, the Bogovsky, we have the full flexibility to choose it once we fix this constant. So yeah, this is an important duality here. And yeah, so actually, so inverting the divergence is a very flexible thing. But what I didn't mention here is, of course, you would also like to have regularity of this operator. So you would like to know that the Bogovsky, not only the divergence is like f, but you also would like to know that the full gradient of this operator is as good as f. So you want to make a harmonic operator out of this, the Calderon-Sigmund operator optimally. And this is the motivation why we need to want to do this. So these are my favorite pictures here. So these are typical fluid domains that we treat in fluid structure interactions. So the fluid is now situated here in the blue part. Here is the solid, so the fluid domain is changing in time because this ball is now falling down. And what one can see here is that, so this is a time-changing domain. So in time it changes, and it is not uniformly Lipschitz. So you see here at the bottom, it essentially becomes a cusp. So you have like a domain which is, for Bogovsky operators, known to be problematic. Yeah? So like a cusp domains, outward cusp domains. So this is not anymore even a John domain, for those who know what this is. I will talk about them later in a second. Yeah, and of course the domain can look much more complicated. And why is this such a good application for our theory is because the Bogovsky operator is, if you wish, the method to get estimates of the pressure in fluids. And here's actually a picture of the pressure. So when you have a ball falling down, then you know that you get a very, very big pressure at this bottom. So we would like to know how large it can be. So this means for this very strange situation, we need to have a Bogovsky, or we would like to have one. So this is somehow the motivation here. I will come to the function spaces a bit later in this talk. So Lubos, this is a seminar about function spaces, of course. So now I will talk a bit about PDEs, yeah, but then I will come back to the function spaces, and they will be actually very, very, let's say, how do you call this? They're not very normal function spaces. They are special ones. Huh? So different. Yeah, we will. Weird. Yeah, no, hopefully not weird. It's a natural with respect to the operator. Yeah, so, but yeah, this is. Making a definition of what you can prove somehow. But yeah, you will see this in a second. Yeah. So here is the Navier-Stokes equation. So there's this divergence here. And here you somehow see that how the gradient and the divergence are coming into play. So this constraint is related to this pressure. There you see this duality again. The pressure actually appears because you look for solutions that are divergence free, which again is the incompressibility of the fluid. Yeah, so because the fluid is incompressible, it creates a pressure, as you, for instance, can observe by taking a hose and, you know, when you suck it, it goes up and down, but it still floats out there. This is somehow this pressure which is created due to the incompressibility. You know this, right? There's the water here, there's the tube, and if you sort of make the water once going over here, it continues running down, and this is precisely the incompressibility which forces the thing to go down. Yeah? So the incompressibility is this, and that is the pressure that is created by it, or vice versa. Yeah, and somehow, yeah, so we have here an external form G, which is something like a gravity. We have a viscosity mu. This is the convective derivative. And somehow the weak form of solution here is that you put everything to the test function, what you can do. And in particular, you put this divergence-free constraint on the test function. So you look at test functions which are divergence-free. And this has the big advantage that this pressure does not appear in your weak formulation anymore, because you get the divergence, gradient dual of the divergence. Yeah? So it vanishes, and you have a very nice weak formulation here where you don't see the pressure. And what usually people do when they prove something for weak solutions for Navier-Stokes, in particular if they have time-changing domains, they say, well, we have a velocity satisfying this. And then they never talk about the pressure ever again. But as we saw in the picture, the pressure is like a very, very important thing in fluid dynamics. It's, I mean, for instance, the heart, yeah, so if you think about applications in the heart, then you need to know, what you want to know is the blood pressure. Of course, you want to know something about the pressure of the fluid. And maybe you, care also about the velocity, but the pressure should not be underestimated. It's just the point I wish to make. And so this is what you usually, I mean, if you are lucky in the papers about this Navier-Stokes on beautiful papers about Navier-Stokes in these time-changing domains, if you're lucky, they mention that you have this equality for the pressure, but usually they don't, nobody talks about the pressure at all. So we wish to change this. And now I show you how to get estimates for the pressure, which actually tell you that the pressure at least is in a maybe beta function space. And so the construction of the pressure as a beta function, you do the following. You use a Bogovsky operator here. And so essentially you define a linear function as this. So you take a test function phi and you map it to the various things that you get on the right-hand side of the Navier-Stokes equation, which is not the pressure. So these are all the other parts, right? Yeah. So, but these terms, they somehow should create the pressure when they act on something which has a divergence. And this is how we define it. So we take a Bogovsky operator and then we define this functional here. And this functional actually is a pressure. And you see this in the next. So actually, so this is a definition of the gradient. So the definition of the gradient of pi acting on the function psi is precisely this map. Yeah. And then when you take a general test function, you can correct the divergence by this operator and you get the weak formulation. Yeah. So this is how you create the pressure using Bogovsky operators. So the Bogovsky induces a functional which gives you the pressure. So what we need is, now in order to know something about the pressure here, we need to estimate these terms here. And then we can maybe take the supremum over all phi's in these various spaces. And this then creates an information about the pressure. So somehow by duality, you get then the information on the pressure. And so you would like to have an operator B, where you can get estimates on all these things. Derivatives, second derivatives, time derivatives. In particular, you want to have this time derivative here, which is somehow weird because it is a space operator, but you still need it for this application. Okay, so this was, I think, the PDE part. Let me just say that there are further applications. Okay, somebody wants, should we look?
Oh, maybe. It's nothing. Camera with the speaker is off. Okay. So, shall we do? Last time we somehow managed. Is it on again?
So at the bottom enters your screen sharing thing. Go over this.
Yes, but jo, tady. Jo, tady start video.
Chairman.
Yeah. So star chairman. Very good.
So, but now the wrong slide, so I have to I can correct it. Yeah. Okay. So now we have to click here again.
Click it, yeah. Oh,
Okay, so yeah, let me. I just want to mention that the Bogovsky operator can also be used on various other domains that are related to the gradient. So you can sort of dualize Poincare inequalities or Kohn inequalities and other things. So it is this is of course my favorite application for the pressure, but there are many or more. Yeah? And what is also interesting, it's very relevant for compressible Navier-Stokes equations as well, which one maybe would not guess, but you need it. Okay, so these are like the time-independent domains. This is the background. So what was known before we started working on this? And so this is like Bogovsky's theorem, if you wish. It was probably proved by somebody else originally, but nevertheless, this is what it's known for. So you subtract somehow the mean value. You can do this in a smooth way or whatever. And then, as long as you have this compatibility condition, and then you have a very nice operator, which is linear, which is Calderon-Zygmunt type. Yeah? So full regularity improvement. And you can solve the divergence in such a way. And the nice thing is that so you have this reference cube. And once you fix this reference cube, so for any set which is star-shaped with respect to this cube, you conserve the zero boundary values. And this is the zero boundary values is really like the important thing of the Bogovsky. Yeah? That you have zero boundary values is the nice property of the Bogovsky. The regularity is also a nice property, but this is also true for the Stokes operator, for instance. Yeah? The zero boundary values is the extra information, if you wish. Okay, yeah, and so we call this is actually, you can write this as a Calderon-Zygmunt kernel even, and we call this kernel the Bogovsky integral, and the inverse is then called the Poincare integral. This is the inverse of it, yeah? So how to do this? And here is like, here are some statements. So once you can do star-shaped domains, you can maybe do some kind of partition of unity, use the fact that every Lipschitz domain can be written as a unit of finite star-shaped domains, and get Bogovsky operators for any Lipschitz domains. And if you then know a bit more, then you know that actually John domains are iterative Lipschitz domains or something like that. I mean, an extension of the natural extension of the Lipschitz domain. And then you can also get Bogovsky operators for John domains. Here somehow the theory for some reason was restricted to this mapping from LP to W1P, but essentially for these domains you have like a Bogovsky on any scale. It's possible to get it. And yeah, so there are two different ways to get it. One by Acosta Duran and Muschietti, which goes by duality of the gradient approach. I will talk about this in a second. And then there's a second approach which uses Wigner decompositions, which is by Diening, Užička, Schumacher. Both are super nice papers, both are super good ways of proving these things. And somehow our result is a combination of the two. But somehow both ideas were important, which is very nice that there were two different ways to prove something, but we could combine it and maybe refine things even more. Yeah. And somehow this construction here from Acosta, Duran, and Muschietti is quite flexible, and you can sort of use the same construction on arbitrary bounded domains, and then you get in some suitable weight in an implicit form. Video is off again. Maybe check if the cable of the camera is incorrectly. Maybe that. No. So let's take it out and then again, yeah?
The alcohol, direction,
Well, I think you still see the shared screen, right? So now I know why it's Zoom only. This is yeah, we continue further. Okay, and somehow what is sort of more going in our direction, what we wanted to include and discuss. So we were like heading towards Hölder domains. So there are also some results for planar Hölder domains using essentially this Acosta-Duran-Rus technique, and also for then S-John domains, which are essentially fractal completions of the Hölder domain. So like the Lipschitz domains connect to the John domains, the Hölder domains connect to the S-John domains. So this is coming this way here. Okay, and
what I can do, you can use this thing here.
Yeah, that's a good idea. That's what I wanted to do.
Just a second. This iPad. Ah, here, right. So,
yeah, hi. Good.
Here.
Ah.
Good.
Oh,
yeah, perfect, perfect. Okay. Good. So now one click and one click back. So, and somehow this is the idea of Acosta-Duran et al. And so you, okay, what can you do? So here you see the flexibility of the Poincaré. Why knowing the gradient, you know everything. So you can map the gradient to the function in many, many ways. So if you look at the mapping, gradient f maps to f, you have many, many ways to do this. And here's one way to do it. So you want to have f at x, so you integrate it to the point z, and then you look at all this, use the main theorem of calculus for several times, at least for this, and then this is actually, as a result, you get the f at fx minus the f of z, essentially. Yeah? And so if you do this now over all members over a ball, and you assume that the mean value over this ball is 0, and by this integration, we have this mapping here as a kernel. Yeah, and using that, so you do this now over B, and then when you integrate over B, then the f of z over B is 0. This is this mean value assumption that you're 0 in the mean value, and then so essentially this, as a result, is equal to f. So you have mapped the gradient of f, put it into this kernel, and produced f. Why do we do this? Well, because we want to dualize it to get the Bukowski. So once you have a kernel, you can look at the dual of this kernel, and this necessarily is a Bukowski operator. And actually, by doing this, you get a quite explicit form. So essentially what you do is now you used to integrate from here to there over all these points. And now what you do for the dual one is you integrate over this blue line, blue occasion here. And you can see now, the closer the x goes to the boundary, the smaller this region becomes. So at the end, you get 0, which is the 0 boundary value which we want for the Bukowski operation. Yeah? So this is like this idea here. You look at some mapping which maps the gradient to the function, then you dualize this kernel, and then you have a Bukowski operator automatically. Good. So this is how you can get the Bukowski kernel. And the nice thing is that these kernels, which you can construct in this way, they are of Calderon-Zygmunt type, so they have the right growth condition. And moreover, by this picture, essentially, you see that the support is like restricted to the region where you can catch something. So in particular, when you are here, for points here, you see that somehow is everywhere 0 boundary values. But if it would go like this, then maybe you would capture a region here for this point, and then it would not be 0 anymore. Yeah, so here you see how the Lipschitz condition or the star-shaped condition makes it 0 boundary value, having 0 boundary values. And yeah, so somehow what we can think about is a time-changing domain, which is uniformly star-shaped, which is just moving, let's say, maybe in the radial direction in the Lipschitz way. Then for such time-changing domains, you can always use the same Bukowski operator, so the operator would not have a time derivative. I think, Michael, this is what we use at some point, right? Yeah. So essentially, as long as you have motions which don't destroy these star-shaped properties, you can use the same operator. Of course, this changes dramatically once you leave the realm of Lipschitz, essentially. So here's like the picture. So if you have a John domain now, this is a bit weirder domain, you can do something similar, but you have to choose a different Poincaré integral, essentially. So if you now want to integrate here, mapping, this is again finding a mapping that maps the gradient to the function, because the dual of this is then a Bukowski operator. So what you do is, okay, you again choose a path, you again take a mean value over these balls, and then you produce a respective Poincaré integral. This you can then dualize. So for this you need some curves, which you have. This is one possibility to define a John domain. And if you dualize this, then I like this picture very much. Then you get something crazy, you don't care, but it still has the right properties that if you get close to the boundary, you will get only a smaller and smaller region. And this was essentially the Acosta-Storan trick to get the general Bukowski operator by using these curves. Assuming that the domain has these curves, then by these curves you can construct a Bukowski operator. Okay, so this is like the story. So here we have like the John domain. And so why does it not, this construction doesn't it work good for us when we have time-changing domains? Now you should really think about time-changing domains that are maybe only Hölder continuous in time and Hölder continuous in space. That's something horrible. And the first one is that this construction is rather implicit. This is the biggest problem for us, actually. And we tried many things there and found the solution eventually. And the second one is that actually somehow the John domain's condition is not that general, in particular when we think about this example of the falling ball. This is a bit like this example here. And you have not included this, so we wanted to have something more general in some ways. Okay. So how does it continue here? Is it already the main result? Yes, it is. Okay, so let's move here nevertheless. So this is a bit of a definition now here. We have two properties that we want to assume for our domain. So we assume that our domain is C alpha beta. So it's alpha Hölder continuous in time and beta Hölder continuous in space. And we also assume, this is like the strictest assumption, if you wish here, that we can locally write it as a graph of a time-space function. Locally, but we need locally to be a graph of a time-space function. And further, we have introduced this number theta because essentially it's not only the regularity of the domain that matters, but also a bit like sort of the gradient of the of the domain which matters, and this is like summarized in this theta function, saying sort of, okay, it's a bit like a house of dimension. Okay, this is of course too rough, but I mean, how much area you cover with your domain. So essentially, if you know that this is a hypersurface of some way, then this would, the theta will always be 1. Yeah? So this is the second parameter that we introduced. And then finally, we have this local, this zero mean condition, which means that for each time value, we have no mean value, which was our compatibility condition. Okay, here's the result now. Yeah, it's horrible. And now these are the function spaces which we consider. So the natural thing here is weighted functions, and with a weight that depends on the distance to the boundary, because somehow it is very essential how the Bogovsky operator will go to the zero at the boundary. Huh? And yeah, so essentially this is our theorem. So we found the Bogovsky operator. The nice thing is we can treat here any alpha beta Hölder domain, and we can always find such an operator. We always have an estimate, and if the domain satisfies, I think satisfies Hardy estimates. Yeah. So if the domain satisfies Hardy estimates, you can get rid of these, exchange them for derivatives, and get back the same estimates as you know to happen for Lipschitz domains. So somehow these weights here appear naturally when you go away from Lipschitz. What is very interesting here is that so these weights, they get worse and worse the lower the order is. So somehow what Hardy inequality tells you is you can sort of get distances for derivatives, but if the domain is horrible, you cannot exchange them anymore. So then the lower order terms are somehow worse than the higher order terms with respect to this funny metric. So yeah, I would encourage people from function spaces to study these spaces here, what can be done there. Yeah, so it's very funny. So you have higher order, so when the gamma is like smaller than the k, so if it's lower order, then you get here a weight which is maybe worse. And the same also for the time derivative, it's even more dramatic. And so why do you get this? So essentially, this comes by the construction, and the construction is very simple. So here's one example that sort of shows that it can also be used. So essentially, if you know that the function has some good properties, but the time derivative is rather weak, because the lower order is more important in the estimate, you can sort of get still that the time derivative of this Bogovsky operator is rather good having these conditions. Yeah, so you can really, I mean, this is also something which we did not make like, how do you say, systematic. Yeah. I mean, often in PDEs, you have like on lower order terms, much more information than on higher order terms, in particular with respect to the time derivative. So you know a lot about the solution, but very little about the time derivative. And somehow this works for this operator here very well. And so somehow this theorem actually here was the thing that I said, okay, only now we can send it to a journal. Yeah, so it's somehow useful what we do here. And yeah, so this is of course my favorite application. So you somehow get some information on the time derivative of the Bogovsky, which is reasonable in many settings. And here's the construction. So our assumption was that we have a graph, and I told you this is an important assumption for this construction. And somehow here's the Bogovsky operator. Okay, this is the partition of unity, making it locally graph, blah, blah, blah. But this is the operator. So the En means that it's just the nth component. And the En is assumed here to be this direction in which you have the graph. So you do the most naive thing in the world. I hope you can see that. It took us 3 months minimum to find it. And then at some point I wrote to Ollie this paper where I wrote this, called it the trivial Bogovsky. Somehow the trivial Bogovsky worked. It was a big surprise for us. And so I mean, what is it? Yeah. So if you take the divergence of 0, 0, and here you took some integral from infinity to y, maybe minus. Okay, this is now 2 dimensions, so let's take x and y. And we take this. And you take the divergence of this square, then you just take the y derivative of that guy. It's equal to f. That's it. That's a Bogovsky operator. And it's a fantastic Bogovsky operator because it actually grows extremely well from the boundary. So if this is the boundary point, then you just go linearly down. Yeah? So actually you have a very good slope. You have a very good control how you approach 0. So if it had already a 0 trace, for instance, then it would look like this. You bring one order of distance here. So every 0 you get one more. Yeah, well, so this was the breakthrough somehow. Okay, you have here the 0, here you don't have the 0, so there you need lots of checks. But essentially this is a Bogovsky, which, and this is also nice, so it also has a better differentiability in y direction. In x direction, the differentiability is not so good. So this is what you need to take care of now. And what the Bogovsky operator does, it actually sort of uses here the space to modify by going down. This is a way of seeing this, that you don't only take one line, but you take several lines. Yeah? And here is somehow the way to make this rigorous. So this is like a decomposition localization by partition of unity. And then we used Whitney type coverings. And this is actually what is sort of more like in the spirit of the Dieling-Ružička-Schumacher paper, to take this trivial Bogovsky and modify it later the moment you have some distance to the boundary. And yeah, and this is done by this very beautiful trick, which is, I think, taken from Acosta-Storan again, that you can decompose. So once you have some strange Bogovsky operator, you can decompose the function into objects which have locally a 0 mean by construction, and apply to this object then again a Bogovsky operator which has better smoothing properties on the scale of the Whitney cubes. Okay, this is complicated, but yeah. Somehow at the beginning there was some very simple observation that actually inverting the divergence is integrating. Yeah, this was the observation essentially, and then you can really use all the beautiful machinery that has been developed for harmonic operators to make out of this something, yeah, which is smooth as possible, maybe. And yeah, this is this localization here, taking like local operators on each Whitney cube. And the nice thing is that somehow these objects then allow to get estimates, which somehow are natural with respect to the regularity of the domain. Yeah, so somehow the B prime, this is like this trivial part of the Bogovsky. This has a very good dual also. You have a nice duality, so you can also look at negative estimates. So we also have like estimates in negative spaces. And yeah, the geometry is encoded in the Whitney type covering. So this is also important. We take Whitney type coverings in time space. Yeah, so we can modify in time and space at the same time. Yeah, so what I like a lot about this construction is that actually the full construction is very local. So essentially, if you have like a situation where you sort of know where a singularity is, you can like modify the construction according to the problem there. So you can really localize it. And this actually means that there is a potential that if you give up linearity, if you say, okay, maybe I'm happy with a nonlinear operator, then you can maybe get much more. So when you really sort of combine the knowledge of where the boundary is rubbish with the knowledge where the function is rubbish, when you take like a Whitney covering according to this two, according to the function and according to the geometry, then I think much more is possible. But I'm waiting for a good application to investigate on this. Anyway, I think this is a nice point where sort of one really can have big further refinement, accepting that the operator gets nonlinear. With respect to linear operators, I think it is already pretty good, but I don't know if the function spaces can be refined considerably. So let's have a look at the theorem again. So here, this is like a heavy weight somehow, but if you make all the construction in accordance to this function, then probably this can be done much better. But of course, then it's non-linear. Okay, yeah. I think that's all I wanted to say. Thank you very much for your attention.
So thank you, Sebastian, for this very nice talk. Are there any questions or comments from the audience?
I just probably some kind of nonsense. I was interested how it works. This partition of unity with respect to the Whitney cubes. So Whitney cubes are almost disjoint, yes, except maybe the edges. And but you don't know how they are built. I mean, if you have like annuli or something, then it's easy. Right? How do you do it? Is there any geometric argument or?
Has to be, right? So here's somehow some Whitney decomposition. Okay, no, what I wanted is this one. So this is somehow the nice thing, yeah? So this decomposition here, this produces something which has the same support as this chi. And okay, yeah, but for the Whitney decomposition, you of course need an overlap. Yeah, of course. Yeah. Okay, so let me write this down.
That's the nature of the question.
Yeah. So we have an overlap, but it doesn't matter. So, okay, so the overlap is of course finite. This means with respect to estimates, you get a constant which depends on the overlap.
I guess you might make these diagonal layers or something.
No, I mean, you sort of use it. You say you take it on the domain, which is maybe this size. So it only covers the neighbors, a finite number of neighbors. So yeah. So I mean, the point is like this one touches only the direct neighbors.
Yes.
And since everybody has at most finitely many neighbors, a fixed number of neighbors, you get the estimate with this. But what is more important here is that if you take this divergence of this, and this is a Bogovsky operator here, the B prime, yeah? That you get here a gradient of the chi j with the B prime. And this is the trivial one, so this is just one direction actually. And then when you sum this up, this is 0 because of the partition of unity. And then there's the second part where you have the divergence of the B prime, so you just get F. So this becomes the F. So this is a very clever trick, yeah. And because of this compact supported function in the cube, this has mean value 0 automatically. So you can locally use a Bogovsky.
So it's less simple, not clever.
Yeah.
Thank you.
Yeah,
my mind is that.
Yeah, it's very nice. Yeah. And so somehow all gradients here become distances. And so the distance is the one which we can control because we have like the integral here. So essentially here you have a measure which is the distance. And then you get for gradient, you get 1 over the distance here. And this cancels. This makes it it's a bit like a maximal function, yeah? And that's how you get estimates. So you don't need the gradient to go inside. This is the trick of this construction. So you exchange a gradient for a distance to the boundary. And that's why the main theorem then also has these distances here. Yeah, so these distances is what you get from the derivatives on the partition of unity. Yeah, and one distance you can exchange for the integral of the Gaussian. I think it's very natural everything here. But, yeah.
You have any maximal estimates in that any maximal operators?
Yeah, this is what I wanted to use, but Ollie somehow convinced me. So for the difficult parts, Ollie is the guy. Yeah. So I was doing the integration. Yeah. Ollie was convincing me that we should use Hardy inequalities like sums. Although the one-dimensional Hardy inequalities, yes, this way to sum. It is very similar. I thought also, I mean, I thought it works with maximal functions, but somehow the Hardy one was even better here. Okay. Yeah. So I was very happy that he knew all this. Yeah. But I mean, like heuristically, for a derivative, you get a distance, and this is precisely what you can get rid of with the integration. And if the domain is rubbish, then you get the troubles according to this mismatch of the distance, and this is incorporated here. So you don't get enough distance in some directions. This is the trouble. Good, thank you. There was a question in the audience? Or,
there was a thank you for a nice result. I can show you the message. It was a praise.
Very good.
You should answer this.
Grazie. Okay.
Okay, so are there any other questions?
Ask the distant people as well.
Virtual.
Yes.
Virtual.
Any questions on Zoom?
Don't hesitate to ask. Unmute yourself and state your comments. Please you.
What is the space C, S, and Z?
This was on the slide before. It's the compatibility here, just okay. Okay, you cannot see it, yeah? No. It means that in every time you are mean value free. So in every time you have the compatibility because it's the space divergence it has to be. And so it means slice-wise mean zeros. Yes, slice-wise.
Okay, so there are no more questions. Let us thank the speaker again. Announcement.
So everybody, next week we are going to have a talk by Rupert Frank from Caltech. I don't know the title yet, so, but it's certainly going to be interesting. So please stay with us. All from Prague for today. Thank you.
Thank you.